Hello and welcome back to Chem Clips by Mr. B. In today's clip, we'll be focusing on carrying on the series on developing exam technique, but this time it's going to be an introduction to the topic 2.1.3, amount of substance, where we'll be looking at questions based on the mole. Okay, so let's get cracking on. In the first question, we are told that we need to calculate the number of europium atoms in 0.0019 grams of europium. We're asked to give our answer in standard form to an appropriate number of Sig Figs. So let's identify what is an appropriate number of Sig Figs. Well, in chemistry, if you've got a mathematical question, you need to look at the raw data. In this question, the raw data is 0.0019. In any mathematical question, an appropriate number of Sig Figs would be based on the fewest number of Sig Figs given in the raw data. Now, seeing in this question I've only been given one piece of data, then it must and this piece of data is to two significant figures. I must give my final answer to two significant figures. So I'm just going to write down 2SF. Okay, so how am I going to calculate the number of europium atoms? Well, I've been given a mass of europium. With a mass, we can work out the moles. So the formula used to work out the moles for a solid is moles is equal to mass over mR. So N is equal to M over mR. Now I'm simply going to substitute the information. I know the mass is 0.0019. I'm going to divide it by the mR. The mR of europium, if I have a look on the periodic table, is 152. That is the relative atomic mass. I'm going to stick that into a calculator. We'll see what we get. So 0.0019 divided by 152. And we end up with 1.25 times 10 to the minus 5. Now what I've just calculated here is the moles. So I'm going to write down the units of this, so mole. But this isn't what the question asked. It's asked me to calculate the number of atoms. So how do I go from moles to atoms? Well, in 1 mole, you have to remember that a mole is just a defined number of atoms. Just like a dozen is synonymous with 12, the mole is synonymous with 6.02 times 10 to the 23. So if in 1 mole there are 6.02 times 10 to the 23 atoms, and I've got 1.25 moles times 10 to the minus 5, I'm going to multiply 1.25 times 10 to the minus 5 by Avogadro's number, which is 6.02 times 10 to the 23. So multiplied by Na, where Na is simply 6.02 times 10 to the 23. And let's see what I get. Multiplied by 6.02 times 10 to the 23, and we get 7.525 times 10 to the 18. Okay, so we've got our final answer, but we need to state it to the appropriate number of Sig Figs, which in this case is 2. So 7.525 times 10 to the 18 becomes 7.5 times 10 to the power 18. So that's the number of atoms there are in 0.0019 grams of europium. So where are you going to get the marks for this? You're going to get the marks for working out the moles as 1.25 times 10 to the minus 5, and you're going to get a mark for working out the correct number of atoms as 7.5 times 10 to the power 18, but it has to be 2 Sig Figs. Okay, moving on. Question number 2. Which mass of substance contains the greatest number of atoms? Again, it's another Avogadro's constant question, much like what we've just done now, but in this format, it's only worth 1 mark, and we've got multiple choice. We've got 4 choices. So, what's the easiest way to go about this? Well, because I've been given mass, and I know that I must work out the moles, I need to work out the MR, the relative molecular mass. So in the case of, so if I know that N is equal to M over MR, so for A, for NH3, we've got nitrogen and 3 hydrogens, so the MR of NH3 is going to be 17, so it's going to be 3 over 17. For CHCl3, we're going to have, as my periodic table, 35. Okay, so we're going to have 3 divided by So we've got carbon 12, hydrogen 1, chlorine 35.5, and we've got 3 of the chlorine, so it's going to give us 119.5. For the next sum, for C, I'm going to do mass. In this case, it's 4 grams. I'm going to divide it by the MR of H2S. Sulfur is 32.1. We've got 2 hydrogens, which are 1 apiece, so that's going to be 34.1. And I've got HCl for option D, so 4 grams divided by 36.5. Now, I could follow this up by working out what these fractions are, and then working out the moles calculated and multiplying that by Avogadro's number. However, it's 1 mark, so I want to spend as minimal time as possible. So I'm going to identify these. Now, from these, the question is asking me which will contain the greatest number of atoms, meaning we need to identify, seeing as each one of these is ultimately going to be multiplied by Avogadro's constant, we want the largest fraction. So just by identifying this, we can rule out that 3 divided by 119.5 is quite a large fraction. It's not, sorry, I beg your pardon, it's going to be quite a small fraction, so it's not going to be that. In the same way, 4 divided by 36.5 is larger, it's going to be smaller than 4 divided by 34.1, so it's not going to be that. So we've got 2 options, A or C. So 3 divided by 17 or 4 divided by 34.1, which one's going to be larger? Just from looking at the numerator and the denominator, I can say with a good degree of certainty that it's going to be A. A is the larger fraction. And if I stick that into a calculator, I can most likely confirm that. 3 divided by 17 gives us a number of a value of 0.176 mole. And for the third one, it gives us 4 divided by 34.1, which is 0.117. So that is indeed a lower number of moles, so it's not going to be that either. So the answer has to be A. I'm not going to bother working out the resulting calculation of 0.176 multiplied by Avogadro's number. It's just, there's just no point, there's no use to it. So I'm going to go with A. Again, that would just give you a mark. Moving on, question number 3. This time you're told that you've got a compound of thulium, atomic number 69, that's quite useful, has the following composition by mass. So you've got 30.7% of oxygen, 15.4% of sulfur, and you've been given 53.9% of thulium. State what is meant by the term empirical formula. Okay, so the empirical formula is the simplest whole number ratio of atoms of each element in a compound. So I'm just going to write that down. The simplest whole number ratio of atoms of each element in a compound, and that's going to give me the 1 mark right there. Okay, so determine the empirical formula of the compound. Sure, you're working, and this is worth 2 marks. So let's have a look. We've been given percentages. We've been given 30.7% of oxygen, 15.4% of sulfur, and the rest of which is thulium. To work out what the empirical formula is, we need to work out the moles. To work out the moles, we're going to do mass divided by MR. However, we're not given the mass, we're given the percentage. So what can we do? Well, if we assume that we've got 100 grams of our sample, it turns out that our percentages end up as our mass. So I'm simply going to show my working out like as such, show the elements, show the masses, seeing as we're assuming that we've got 100 grams of our sample. We're going to divide it by the relative atomic mass. So the relative atomic mass of oxygen is 16, sulfur is 32.1. Now thulium, it's given us the atomic number, so it's going to help us identify where it is in the periodic table, and in fact it's in the F block of the periodic table, and it has a relative atomic mass of 168.9. 168.9. We're going to work out the moles from each of these sums. So if I do this, 30.7 divided by 16, I end up with 1.992. We're going to do 15.4 divided by 32.1, and that gives us 0.48, and we're going to do 53.9 divided by 168.9, and that gives us a number of 0.320. Right, okay, so if I've got these number of moles in my answer, I need to work out what the whole number ratio is, because I can't write down O 1.92, O subscript 1.92, S subscript 0.48, TM subscript 0.320, because it's not whole number, they're not integers, they're not whole number ratios. So to work out what the whole number ratios are, I'm going to divide by the smallest number of moles, which is 0.320, the moles of thulium. That's for each one. So for 1.92 divided by 0.320, I end up with a number of 6. For 0.48 divided by 0.32, it's going to be 1.5. Yeah, 1.5. And for the last one, of course, it's just 1. So we've got 6 to 1.5 to 1 ratio. However, again, we've not got whole numbers. 1.5 is not a whole number. So we need to work out, or we need to adjust accordingly. So now what a lot of students tend to do is they'll round the 1.5 up to 2. No, you need to turn it into a whole number by multiplying by a factor. For example, if I multiply 1.5 by 2, I end up getting a whole number ratio. I end up getting a whole number of 3.0. So if I multiply everything in the ratio by 2, so I've got 12 to 3 to 2. So my empirical formula is simply O12 S3 TM2, and that's going to get me my mark. So I'm going to get 1 mark for working out the moles, or showing the working out for the moles, and I get 1 mark for showing the correct empirical formula as a result of multiplying everything by 2 in the whole number ratio. Sorry, in the ratio. Okay, moving on to question number 4. And making good time, I suppose. Yeah, okay, that's fine. 13 minutes. Okay, so we're told that an aqueous solution of aluminium chloride can be prepared by the redox reaction between aluminium metal and dill hydrochloric acid. You're told that a student reacts 0.080 moles of aluminium completely with dill hydrochloric acid to form an aqueous solution of aluminium chloride. You're given the equation, which is super important. Calculate the volume of hydrogen gas in decimeters cubed at room temperature and pressure. So immediately when you see the words room temperature and pressure, your mind should be thinking, okay, room temperature and pressure, there's going to be another equation, because I know that at room temperature and pressure, 1 mole of gas occupies 24 decimeters cubed of volume, I suppose. So the equation to show this is N is equal to V over 24 dm cubed. We're asked to calculate the volume, so we know that okay, so we're asked to calculate the volume of hydrogen gas formed, and yet we're only told the moles of aluminium. So let's have a look at the equation. We've got the moles of aluminium, and we need to compare that, or we need to work out the moles of hydrogen gas. So if we compare that in our equation, we've got 2 moles of aluminium to 3 moles of hydrogen. So we've got a 2 to 3 ratio. Now if I've got 0.08 moles, 0.08 moles of aluminium, how many moles of hydrogen am I going to have if it's a 2 to 3 ratio? Well, let's consider, how do we go from 2 to 3? I simply multiply by 1.5. So I'm going to do the same thing with 0.08, multiply by 1.5. So multiply by 1.5. So I've got 0.08. I don't. Should I be using a calculator for that? 0.12 mole. Okay, so I've worked out the number of moles of hydrogen. I'm asked to work out the volume of hydrogen gas. Now that I know the number of moles, I can stick it into the equation I've already got, and rearrange it ultimately. So we know that V is equal to N times 24 decimeters cubed, where N is 0.12 moles, multiplied by 24 to end up with a volume of 2.88, and that's in decimeters cubed. So you're going to get a mark for working out the moles of hydrogen as 0.12 moles, and you're going to get a mark for the final answer, 2.88 decimeters cubed. Okay, part B. Calculate the mass of aluminium chloride formed. Give your answer to 3 significant figures. So let's have a look. We're asked to calculate the mass of aluminium chloride. And again, we're starting off with the moles of aluminium. So let's consider a ratio between aluminium and aluminium chloride. According to the equation, for every 2 moles of aluminium, we're going to have 2 moles of aluminium chloride. So it's a 2-to ratio. In other words, it's a 1-to-1 ratio. So if I've got 0.08 moles of aluminium to begin with, I'm expecting to form 0.08 moles of AlCl3, aluminium trichloride. Okay, so if I assume the moles of aluminium chloride, or the theoretical moles of aluminium trichloride, ought to be 0.08, and I know that N is equal to M over MR, I could work out the mass by doing N times MR. So M is equal to 0.08 multiplied by the MR of aluminium chloride. So we've got aluminium 27 plus 3 times 35.5. So 35.5 times 3 plus 27, that's the MR. So we get an MR of 133.5. We're going to multiply by 0.08, multiply by 0.08, and we end up with 10.68 grams. However, we have calculated the mass of aluminium chloride. What we haven't done is give it to 3 significant figures. So that's going to be 10.7 grams. We're going to get the 2 marks for this. Well, again, you're going to get a mark for working out the MR, 133.5, and 1 mark for consequently giving the answer to 3 significant figures as 10.7. Okay, next question. Calculate the volume in centimeters cubed. And this time we're not doing in decimeters cubed, it's in centimeters cubed, of 1.20 mole per decimeter cubed of hydrochloric acid needed to react completely with 0.08 moles of aluminium. So let's have a look again at the equation, and let's consider the ratio between aluminium and hydrochloric acid. So for every 2 aluminium, we've got 6 moles of hydrochloric acid which are reacting. So we've got a 2-to-6 ratio. So we've got Al to HCl, it's a 2-to-6 ratio. I know I'm starting off with 0.08 moles, so therefore to work out the moles of hydrochloric acid, to go from 2 to 6, we need to multiply by 3. So I'm going to do 0.08 multiplied by 3, and we've got the theoretical number of moles that ought to react completely with 0.08 moles of aluminium. So that's 0.24 mole of HCl. Okay, so now we're considering moles of solutions. So when you're considering moles of solutions, you have to use difference relationship. We know that moles is equal to V times C, where however, we need to be really careful. V is in decimeters cubed. So N is equal to VC. Okay, so I want to work out the volume of hydrochloric acid. So V is equal to N over C. We know the moles as 0.24 for HCl. We know the concentration is 1.20 moles per decimeter cubed. So 0.24 divided by 1.2 and it gives us 0.2. Now remember, this is in decimeters cubed. To convert between decimeters cubed to centimeters cubed, you multiply by 1,000. So that's going to be 200 centimeters cubed. Now for this question, you're going to get a mark for working out the moles of HCl as 0.24, and you're going to get a mark for working out the volume to 200 centimeters cubed. Always consider what units you're asked to work out or state your answer in. And it says it in the question twice. Okay, moving on. Question number 5. What is the molecular formula of the compound below? So we're now given a skeletal structure and we need to work out how many carbons there are, how many hydrogens there are. Okay, so I'm going to start off with identifying that each point is a carbon atom. So we've got 1, 2, 3, 4, 5, 6, 7. We've got 7 carbon atoms, so C7. Now we know that carbon must have 4 bonds. Okay, so starting with the carbon at the top of the pentagon, right, I forgot what a 5-membered ring was called. Okay, so at the pentagon, so we've got 3 bonds. So that means we've got 1 hydrogen, just 1 for that carbon there. That's attached. The next carbon on the left hand side, we've got 2 bonds. So that carbon's got 2 bonds, it must have 2 hydrogens, so that's 2 hydrogens there. The next carbon moving along, again, it's got 2 bonds, so that ought to have 2 hydrogens. Next carbon along, it's got 2 bonds, so it must have 2 hydrogens as well. Next carbon along, it's got 3 bonds, so it must have 1 hidden hydrogen. The carbon on the right hand side of the methyl group, it's got 3 hydrogens, 1 bond. Again, starting off with the methyl group at the top, it's got 1 bond, so it must have 3 hidden hydrogens. So if we total that up, 3, 6, 8, 10, 12, 14. So C7H14 is our molecular formula. Remember, molecular formula is the actual number of atoms of each element in a molecule. So we've got C7H14, so that gives us the answer as C. Be very cautious when it comes to this sort of question. What students tend to do, they'll forget about how many bonds there are. They won't count the number of hidden hydrogens correctly, so do take care. Okay, moving on to the last question, 6, and you're told that this question is about chemicals used by gardeners. You're told that a garden product contains hydrated ammonium iron 2 sulfate, which has this ridiculously long formulae. You're told that this hydrated ammonium iron 2 sulfate contains 27.55% by mass of water of crystallization. Calculate the value of X in this formula. Show you're working out, and this is a free marker. So this is a slightly tricky question. It did appear in an A2 paper, in the unified paper in year 13. However, it's something that you should still be able to tackle even in year 10. So we're going to use a principle very similar to what we did already when we worked out the empirical formulae. Because we're given a percentage by mass, we're going to assume we've got 100% of our hydrated ammonium iron 2 sulfate. If we assume we've got 100%, then we're stating that 27.55 grams must be water. So we're going to work out the moles of water. So N of H2O is equal to M over MR. We know that the mass, assuming that we've got 100%, sorry, not 100 grams, is going to be 27.55 divided by the MR of water, which is 18. So if we do that, we get 27.55 divided by 18, and we end up with 1.5305 mol. Okay, so we're going to work out the moles of our ammonium iron to sulfate. I'm just going to write down our salt. I'm not going to bother writing either the entire name or the formulas. It's going to take me ages. So the mass of that, what is the mass going to be? Well, again, we're assuming we've got 100 grams. Therefore, if I had 100 grams in total, of which 27.55 is water, it so follows that the rest of it, 100 minus 27.55, is going to be made up of the salt. Okay, so 100, that's equal to... Okay, 72.45, and we need to divide by the MR of this insane salt. Okay, so a mole NH4 has a mass, also has a MR of 18. We're going to multiply that by 2 because we've got 2 ammoniums. Iron is 55.8, so plus 55.8. Sulfate is 32.1 plus 4 oxygens. Each oxygen is 16, so 16, 32, 64 plus 64. I'm going to multiply this last one by 2 because we've got 2 sulfates. So if I do that in my calculator, I'm going to get 18 times 2 plus 55.8 plus 32.1 plus 64, and we're going to do that sum twice. I'm not sure, showing it a different way in my calculator would have been easier. 64, and we get 284 for the MR. So 72.45 divided by the answer gives us 0.255 mole of our salt. So we've got the number of moles of our water, and we've got the number of moles of our salt. What are we going to do? Well, we're going to work out a whole number ratio to work out what the value of X is. So let's work out what the ratio between the two is. I'm simply going to do 1.5305 divided by answer, and it gives us 5.99. So that's telling us that the value of X is going to be 6.0. Done. Okay, I hope... Oh, let's work out where we're going to get the marks for this. We have shown that earlier, haven't we? Yeah. Okay, so we're going to get a mark for working out the number of moles of water. We're going to get a mark for working out the number of moles of our salts, or our hydrated ammonium to iron, whatever it was now. And we're going to get a mark for working out X. So that's 3 marks there. I hope that was useful. Until next time, bye.